welcome students. This is the second lecture of unit number 4, and the topic for today's lecture is two compartment open model. Okay. In the previous lecture I have told you about the representation of the two compartment model, the various models of model 1, model 2 and model 3 on the basis of the elimination that is that takes place from the compartment. Okay. So, in this I will tell you about the kinetics of the plasma of the drug in case of the IV administration. Okay. So, if we talk about the IV bolus kinetics, and this is the central compartment, okay, this is the peripheral compartment. As I have told you in the previous lecture, in case of two compartment open model, there will be two different compartment, one is the central compartment and second one is the peripheral compartment. Okay. So, if we want to represent the plasma drug concentration in the central compartment, I am representing it with the help of Cp. This Cp is the plasma drug concentration in the central compartment, this Vp is the volume of distribution or the volume of the drug that in the central compartment. Okay. Now, this Ct is the plasma drug concentration in the tissue compartment, or we can say peripheral compartment, and Vt is the volume of drug distribution of the tissue compartment or peripheral compartment. Okay. So, in the two compartment model, as we are talking about the IV bolus kinetics, so drug is already available in the central compartment, or we can say the blood, and from here the drug has to get distributed into the various peripheral compartments, or we can say the tissue compartments. Okay. So, from the central compartment drug is getting distributed, or drug is moving from the central compartment to the peripheral compartment with the rate constant value of K12, and from the peripheral compartment it is coming to the central compartment with the help of the ratio K21. Okay. And the elimination is taking place from the central compartment, and we are representing it by constant K. Okay. So, what is the K12? It is the rate constant of the drug movement from the central compartment to the peripheral compartment. What is K21? It is the rate constant of drug movement from peripheral compartment to the central compartment. Now, what is the K? This is the first order elimination rate constant. Okay. So, these are the various designations. Now, coming on the kinetics. So, this is the d by dt of Cp, means the rate of change in the plasma drug concentration. Now, to calculate what is the effect of the time on the plasma drug concentration, or what is the amount of drug in the body per unit time, we can calculate with the help of this equation. The rate in minus rate out means the rate of change in the plasma drug concentration with respect to time we can calculate by the rate at which the drug is getting entered into the central compartment, or the drug is getting entered into the body, and the rate at which the drug is leaving from the body. Okay. So, to calculate the rate of change in plasma drug concentration with respect to the time, we can calculate it by the by subtracting the rate out from the rate in. Okay. So, if we talk about the plasma drug concentration that is available in the central compartment, in case of central compartment, the value of plasma drug concentration will be equal to the rate at which drug is reaching into this central compartment minus the rate at which the drug is leaving from this compartment. Okay. Means to calculate the rate of change in plasma drug concentration with respect to the time, we have to subtract the rate out from the rate in. Okay. So, when we talk about the plasma drug concentration in the central compartment, or we can say d by dt of Cp, then we can represent it by like this. Then how we are representing this? Because I have already told you that from the central compartment drug is getting moved into the peripheral compartment. Okay. And the constant that is used is K12 and K21. and from here the drug is getting the drug is leaving it, from the central compartment. Okay. So, how the drug is getting into the central compartment. Okay. The drug is entering into the central compartment by the constant K21. Okay. We want to write the rate in minus rate out. Okay. In the central compartment, the drug is getting in with the help of this constant, that is the K21. That is why we have written K21. Okay. And drug is getting reached into the central compartment from where? From the peripheral compartment. So, we can say this CT is getting reached into this compartment with the help of this rate constant, that is the K21. That is why we have written K21 into CT. Okay. This is representing the rate in. This is the rate in. Now, if we talk about the rate out. So, as it is already represented that the drug from the central compartment is leaving with the help of two constant, one is the K constant and second one is the K12. Okay. So, we can write it K12 Cp plus KCp. Why we have written like this? Because the from the central compartment the drug is getting leave. From here the Cp is leaving this compartment with the help of constant K, and from here the Cp is leaving from the central compartment and reaching into the peripheral compartment with the help of constant K12. Okay. That is why we have written rate in minus rate out. This rate in is K21 Ct. This K21 Ct is representing the value of rate in, and K12 Cp plus Kcp is representing the value of rate out. Okay. So, this is all about the plasma drug concentration in the central compartment. Okay. Now, if we want to measure the rate of change in plasma drug concentration in the peripheral compartment, then also this rule will apply, that is the rate in minus rate out. Okay. So, if we talk about the peripheral compartment, then here in this peripheral compartment the drug is coming from the central compartment with the help of constant K12. That is why the concentration, the rate in can be written as K12 Cp minus, and the drug from the peripheral compartment it is leaving and it is reaching into the central compartment with the help of constant K21. Okay. So, that is why we will write K21 Ct. Okay. So, this is the plasma drug concentration into the peripheral compartment, or we can say the tissue compartment. Okay. So, now what is plasma drug concentration? It is the amount of drug that is distributed in a body, or it is the amount of drug in the body divided by volume of distribution. Okay. So, we can write Cp. Cp is the plasma drug concentration in the central compartment. That can be written as dP. dP is the amount of drug in the central compartment divided by Vp. It is the volume of distribution into the central compartment. Okay. So, Cp can be written as Cp is equal to dP upon Vp. Cp is equal to dP upon Vp. Okay. Similarly, we can write the Ct. What is Ct? It is the dt upon Vt. Why it is written as dt and Vt? Dt is the amount of drug into the tissue compartment and Vt is the volume of distribution into the tissue compartment. Okay. So, we can put these value of the equation number 3 and 4 into the equation number 1 and 2. Okay. So, when we put the values of Cp and Ct, we will get another equation, that is equation number 5 and the equation number 6. Okay. So, in the equation number 5, what we are getting, d by dt of Cp is equal to K21 into dt upon Vt minus K12 dP upon Vp minus Kcp. Okay. So, why we have written like this? These are the values of these values we are putting into these equations, and when we have put these the value in these equation, we are getting the equation number 5 and 6. Okay. So, the equation 5 is K21 dt upon Vt minus K12 dP upon Vp minus Kcp, and equation number 6 is d by dt of Ct is equal to K12 dP upon Vp minus K21 into dt upon Vt. Okay. So, when we solve these two equations by using the Laplace transform and the matrix algebra, we will get another equation, equation number 7 and 8, and these equation will describe the change in the drug concentration in the blood and also in the tissues with respect to the time. Okay. So, by solving the equation number 5 and 6, we are getting the equation number 7 and 8. Okay. So, equation number 7 is d naught p upon Vp into K21 minus alpha into e raised to power minus alpha t upon beta minus alpha plus K21. Okay. This is the equation number 7 that we have get from the by solving the equation number 5, and this equation 8 we are getting by solving the equation number 6. Now, what is this term d naught p? This d naught p is the dose that is given the intravenously, because we are talking about the IV bolus kinetics. So, we are representing the dose by d naught p, that is we have given the dose by intravenously. Okay. Now, t is the time after administration of the dose, and these alpha and beta, these are the constants that depends on the values of K12, K21 and K. Okay. As I have already told you about the constant K, K12 and K21. So, the alpha and beta, these constant will depend on the values of K12, K21 and K. Okay. Now, the rate constant for the transfer of drug between the compartments, we can call them as micro constants or the transfer constants. Okay. So, what is the significance of these constants? These constants are relating the amount of drug that is being transferred per unit time from the one compartment to the another compartment. Okay. So, the values of these compartment or the values of these constant we can estimate by the graphic method. Okay. So, if we want to calculate the value of these constant, the alpha plus beta, the value of alpha plus beta is equal to K12 plus K21 plus K, means the sum of the constant, that is K12, K21 and K is representing the sum of the alpha and beta, and the multiplication of alpha and beta, the multiplication of these micro constant is representing the K21 K. Okay. So, the constant, these constant alpha and beta, these are the hybrid first order rate constant for the distribution phase as well as for the elimination phase. Okay. So, the equation number 7, this equation number 7, this equation number 7 can be modified, and by solving this equation number 7, we are getting another equation, that is Cp is equal to A into e raised to power minus alpha t plus b into e raised to power minus beta t. Okay. So, as I have told you, these alpha and beta, these two are the rate constant for the distribution phase and the elimination phase. Alpha is representing the distribution phase and beta is representing the elimination phase. Okay. Now, what about this constant A and B, this capital A and capital B? These two constants are the intercept on the y axis for the each exponential segment of the curve. Okay. In this, we can get a bi-exponential curve like this. Okay. So, if we extrapolate this, then we will get the two constant, that is constant A and constant B. Okay. So, the value of these constant A and B we can get by the method of residual or by the computer method. Okay. So, the formula for calculation of constant A is equal to d node upon alpha minus K21 upon Vp into alpha minus beta. The value of B is d node into K21 minus beta upon Vp into alpha minus beta. So, with the help of these two equations, we can get the value of A and B. Okay. So, these A and B are the empirical constant that are directly proportional to the dose administered. Okay. So, these are the value of A and B. Now, if we want to calculate the value of K21, K12, then the formula for calculation of K21 is K21 is equal to AB or A beta plus B alpha upon A plus B. Okay. This is the formula for the calculation of constant K21. Now, if we want to calculate the value of K12, then the formula is AB into beta minus alpha square upon A plus B into A beta plus beta A beta plus B alpha. Okay. So, this is the equation for the calculation of rate constant, that is K12. Now, the method of residual. Now, what is this method of residual? This method of residual we can also say it as the method of feathering or peeling or curve stripping. So, it is a very commonly used technique for resolving a curve into the various exponential terms. Okay. Because I have told you previously, as I have told you that in the two compartment model we are getting a bi-exponential equation. So, by converting this bi-exponential term into the single term, we can get the values of different constants. Okay. So, in this method of residual, we are fitting a curve to certain experimental data of a drug when drug is not clearly following a one compartment model. Okay. It is very easy to get the plasma drug concentration in case of one compartment model, because the drug is behaving or drug is representing a single term, drug is representing a single exponential line. But in case of two compartment model, we are getting two lines. That is why we are converting the bi-exponential term into the into certain experimental data. Okay. So, with the help of this IV bolus kinetics, we are calculating 4 different parameters: apparent volume of distribution, biological half life, elimination rate constant and AUC. Now, what about the method of residual? In case of method of residual, what we are doing, as I have told you, Cp is equal to A e raised to power minus alpha t plus B e raised to power minus Bt. This is the equation. So, if we want to what we are doing in the method of residual, we are reducing this equation into a single term. Okay. So, this A, this is representing the distribution, this is representing the distribution, and this is representing the elimination. Okay. So, when full distribution has takes place, after the full distribution there will be only elimination process. Okay. So, when the full distribution takes place, this equation will be reduced to this. After the full distribution, this equation will be reduced to this, because distribution has already takes place. Okay. So, to get the value of this B constant, what we can do? When the distribution has takes place, so the Cp will be equal to B e raised to power minus Bt, and when we take logarithm on both sides, then what we will get? Logarithm of Cp is equal to logarithm of B minus beta upon 2.303. Okay. So, in this we can plot a curve that is between the logarithm of Cp and t will be on the x axis, and we will get a this type of curve. Here the intercept is representing the value of logarithm of b and the slope is representing the minus b upon 2.303. Okay. Now, what about the value of a? So, when we subtract the value of this from the total value, then what we will get? We will get the value of a, or we can say if we subtract Cp dash from the Cp, we will get the value of a. Okay. So, what we will do? We will subtract this Cp dash from this. Okay. So, what we will get? We will get the a e raised to power minus alpha t plus b e raised to power minus beta t minus b e raised to power minus beta t. So, this term will get cancelled. Now, by taking logarithm, what we will get? We will get the logarithm of a minus alpha upon 2.303. Okay. So, this is the equation for the calculation of the value of a. Okay. In this, when we plot a curve, what we will get? Cp minus Cp dash will be on y axis, t will be on the x axis, and similarly we will get a curve like this. This value, the intercept is alpha upon 2.303, this value is logarithm of a. Okay. So, with the help of this method of residual, what we are getting? We are getting the values of different constant, or we are getting the value of a and b. So, with the help of this method of residual, what we are doing? We are converting this bioexponential term into a simple terms, and we are calculating the values of these constant a and the b, and this a is representing the distribution phase and b is representing the elimination phase. Okay. So, using this we can also calculate the biological half life. Okay. So, if we are having this equation, then to calculate the biological half life, what we will do? As we all know, T half is equal to 0.693 upon the rate constant, that is k. So, if we want to calculate the biological half life, what the formula will be? T half is equal to 0.693 upon b. This is the formula for the calculation of the biological half life. If we want to calculate the AUC, that is the area under the curve, then the equation will be AUC is equal to A upon alpha plus B upon beta. This is the formula for the calculation of the area under the curve. Okay. So, in this way we can calculate the different values of different parameters by using this two compartment model IV bolus kinetics. Okay. So, this is all about this lecture. In the next lecture, I will continue with the another topic of this unit number 4. Okay. Thank you.